Hello class, welcome to Stat 1200. I am your instructor, William Buellman, and today we're covering section 11.2, the least squares regression line. Our objectives for today are to compute the least squares regression line, use the least squares regression line to make predictions, and interpret predicted values, the slope, and the y-intercept of the least squares regression line. The table below presents the size in square feet and selling price in thousands of dollars for a sample of homes. In the previous section, we concluded that there is a strong positive linear association between size and sales price. We can use these data points to predict the selling price of a house based on its size. The figures below present scatter plots of the previous data, each with a different line superimposed. It is clear that the line in the figure on the left fits better than the line on the figure on the right. The reason is that the vertical distance are, on the whole, smaller. The line that fits the best is the line for which the sum of the squared vertical distance is as small as possible. This line is called the least squares regression line. Given ordered pairs in X and Y format with sample means X bar and Y bar, sample standard deviations of Sx and Sy, and a correlation coefficient of R, the equation of the least squares regression line for predicting Y from X is given by Y hat is equal to B naught plus B1 times X, where the slope is B1, which is equal to the correlation coefficient R, over the sample standard deviation of X divided by the sample standard deviation of Y. So again, that's R times Sx divided by Sy. And the y-intercept is B naught, which is given by Y hat, our predicted value, minus B1, which we found already as the slope, and X bar, which is the sample mean for X. The variable we want to predict, in this case, sell price, is called the outcome variable. Or the response variable. And the variable we are given is the explanatory variable. Or the predictor variable. In the equation of the least squares regression line, X represents the predictor variable and Y represents the response variable. So in this case, you're going to use X to predict Y. So X is whatever you're using to predict, and Y is going to give you that response or outcome. So in this case, if we were to use this right here, let's say, as our prediction value, we would expect that right about there is where our response variable would be. Let's do an example. Example 1. Compute the least squares regression line for predicting sales price from size. So from that example that we did before, we're going to compute the least squares regression line for it. First, we'd compute the sample mean, standard deviation, and correlation coefficient, which gives you the following values. So the sample mean for X is about 2,891. The sample mean for Y is about 447. The sample standard deviation for X is about 269. The sample standard deviation for Y is about 29. And R, the correlation coefficient, is about 0.9. The exact values are listed right there. The slope of the least squares regression line is B1, which is equal to the correlation coefficient times the standard deviation of Y divided by the standard deviation of X, which gives us 0.9005918 times the sample standard deviation of Y, which was 29.68, 0.405 divided by the sample standard deviation of x, which is 269 times 49,357, which equals 0.09919,796. So that is B1, which is the slope of the least squares regression line. It is about 0.09. So now we're going to find the y-intercept, which is B0, which is given by y bar minus B1 times x bar. So we have 447.0 minus 0.09919,796 times x bar, which is 2891.25, which equals 160.1939. So you guys can see in this example, I'm carrying a lot of decimal places. So make sure you do that. Carry extra decimal places because there's going to be a lot of rounding error if you don't, and that will create incorrect answers. So carry quite a few decimal places. As in my example, I'm carrying 7 decimal places where appropriate. So carry a lot of decimal places. All right. So now that we have the y-intercept, the equation of the least squares regression line y hat was given by b0 plus b1 times x. So we just fill in everything that we have. We know b0 up here was 160.1939. So we know b1, which is 0.0992. So I'm going to round to 4 decimal places there because b0 is in 4 decimal places. So I'm going to take b1 to 4 decimal places as well, times x, because x is what we're going to plug in to get the y value. So you can see here we have b0, which is our y-intercept if you think back to algebra. We have b1, which is our slope if you think back to algebra. And x is still going to be our prediction variable. So for whenever we plug in an x, we will get a y hat that corresponds to it, which gives us a response for our predicted value. We can use the least squares regression line to predict the value of the outcome variable by substituting a value for the explanatory variable in the equation of the least squares regression line. This is what I was just talking about in the previous example. If you take a predictor value and you plug it into that equation for the least squares regression line, you will get an outcome variable that you can use. Example 2. The equation of the least squares regression line for predicting sales price from size is right there as we just found in the previous example. Predict the sales price of a home whose size is 2,800 square feet. So now we have a predictor value and we're going to figure out what the outcome value is using the least squares regression line. So we're just going to plug everything in. So we have 160.1939 plus 0.0992 times 2,800, the square feet we were given. So you see how we just took that predictor value and plugged it in, which when we do all this math, we get 438.0. So if you look at the graph below, you can see where at 2,800 square feet, the y value is going to be 438. So what that means is we expect for a 2,800 square foot home that it will sell for $438,000. The predicted value y hat can be used to estimate the average outcome for a given value of x. For any given x, the value y hat is an estimate of the average value of y hat for all the points with that value of x. So what that's saying is this y hat is what we would expect if you took all the x values that you could possibly get for, in that case, 2,800. If you took the average of all the homes that were 2,800 square feet and what they sold for, we would expect that average value to be 438,000. So that's what that y hat is. It's a prediction of the average value. Example 3. Use the equation of the least squares regression line for predicting sales price from size. Again, we have it. We've used it before, so here it is again. To estimate the average price of all homes whose size is 3,000 square feet. Again, the least squares regression line was 160.1939 plus the slope, which was 0.0992, times whatever our predictor value is, which in this case was 3,000. So we have 160 times 1939 plus 0.0992 times that 3,000, which gives us 457.8. We estimate the average price for a house that is 3,000 square feet to be $457.8 thousand. The y-intercept B naught is the point where the line crosses the y-axis. So that's what that B naught that we found is. If the predictor value was 0, this is where it would cross the y-axis, right? Because where the predictor value is 0, that means x is 0. So that's where it's crossing the y-axis. This has a practical interpretation only when the data contains both positive and negative values of x. If the data contains both positive and negative x values, then the y-intercept is the estimated outcome when the values of the predictor variable is 0. If the x values are all positive or all negative, then the y-intercept B naught does not have a useful interpretation. So if we go back to our housing example, if you were to think of it and go, okay, what does B naught equal there? What does the y-intercept mean? Okay, what it means is what the selling price of a house that is 0 square feet. Okay, can a house be 0 square feet? No. All right, the house wouldn't exist. It's 0 square feet. So this is the case where since we have all positive values, the y-intercept doesn't have a useful interpretation because we can't predict the price of a house that has 0 square feet, interpreting the slope. If the x values of 2 points on a line differ by 1, their y values will differ by an amount equal to the slope of the line. This fact enables us to interpret the slope, B1, of the least squares regression line. If the values of the predictor variable for two individuals differ by 1, then their predicted values will differ by B1, the slope. If the values of the predictor variable differ by an amount D, so other than 1, then their predicted values will differ by B1, the slope, times D. So however many units apart they are, it's going to be that many units times the slope. Example 4. Two houses differ in size by 150 square feet. By how much should we predict their prices to differ by? So we know how much they differ by. We already have the slope, so we can use this to guess about how much we think their predicted prices should be different by. The slope of the least squares regression line B1 was 0.0992. Thus, we can predict that their values will differ by that 0.0992 times the 150 square feet, the amount of difference in square footage that the properties have, which is going to equal $14.9 thousand. So we expect the house that is 150 square feet bigger to cost $14.9 thousand more, or $14,900 more than the house that was 150 square feet smaller.